We can start. We have short and practically my last lecture of this course. Tomorrow morning I'm flying to a conference, so we will not have normal regular lecture next time. We will have Zoom lecture. I will send you Zoom link, the lecture, and Stephanie will be giving some lecture on something that she's doing, hopefully. We'll see how it goes. So this is last lecture on generic topic related to particle filtering and Monte Carlo methods, which are computational methods very famous in computer science and engineering, used for multiple different things, very universal, and the universality of these methods related to computations of integrals, actually, because we haven't learned directly how to compute integrals with numerical methods. You have millions of different methods for computing integrals, but this is giving you pretty nice approximation, relatively not too complicated. The idea is very simple, relatively simple. And have you learned probability theory? Okay, so this relates to probability theory, but I will not get into the actual depths of the theory behind it, because mathematical formulation for these methods is pretty complicated, even if you know probability theory. But before we go there, do you have any questions on the previous lectures or anything else? All right. So, Monte Carlo methods, it's kind of very interesting topic, unexpected, and was developed by practically one person in collaboration with many other people, but this Polish mathematician, whose name is Stanisław Ulam. He was Polish-American mathematician, and obviously nobody would pronounce his name here, so he called himself Stan Ulam. Kind of not very close to his real name, Stanisław. So he is actually famous for multiple different things, not only Monte Carlo methods. He was one of the developers of hydrogen bomb, which sounds very irrelevant to his field of interest in general. He was participating in the Manhattan Project and the bomb development in the United States when he was here after the Second World War. He also developed multiple other things, so he has also multiple things called on his name. On his thing, which is, again, seems to be completely irrelevant. I have many stories about that guy, fun stories on events. One time he was at some very boring conference, and then he had some napkin, and on that napkin he started to jot numbers in a spiral, like 1, 2, 3, 4, 5, 6, like in a circle around that spiral. And then he started to select, out of boredom, he started to select prime numbers. When he selected all of the prime numbers on that napkin, they started to sit on the diagonals somehow. And you know that prime numbers, they do not have any patterns at all, which is like they almost completely random. They are not random, they are obviously deterministic. But when people are looking for patterns of formulas to calculate them or some sort of rules that you can apply to them, people couldn't find anything which actually works for them. So when he tried, he got some diagonal lines with these prime numbers kind of sticking out in all kinds of directions, which is now called Ulam spiral with those prime numbers. So he had contributions to many different areas of maths and physics, but this one area is where he is the most famous. He, one of the fathers of computers, okay, together with von Neumann, they developed math and architecture of computers. They were first developers, and this is why these methods became interesting only after development of computers, because he lived at the time where there was no computer practically, before computers, like beginning of the 20th century, no computers. Computers arrived probably in 40s. This is where computers started to grow. But before that, no computers, only mechanical, you had all kinds of mechanical mechanisms like from Pascal, arithmometers, that kind of thing. But computers were developed in the 40s of 20th century. So what happened is these methods are not useful by hand because all you need for these methods is random number generator. How would you generate random numbers from particular distribution? This is actually extremely complicated problem in math. How you generate pseudo-random numbers from Gaussian distribution or from uniform distribution. How do you pick that completely randomly? Okay, and people tried millions of different algorithms. They were all not very reliable. So they were repeating themselves after a while if you compute all these numbers, or they were not uniformly distributed or not normally distributed. They had troubles with that, a lot of it, okay? So the main problem was like how you actually generate numbers, which are random numbers or pseudo-random numbers, right? Which are not repeating themselves for million and million numbers. You don't want them to repeat sequence, right? Otherwise they will become repetitive. This is not really random. So these people, like mathematicians of that caliber, thought about these problems and solved that in multiple different ways. And you have multiple different random generators now, which are used in MATLAB, Python, and other programming languages. But before computers became a thing, you couldn't do that. Okay, there was no even way to do that. You couldn't generate 1 million random numbers, pseudo-random numbers. There was no way that you will compute that by hand, right? And if you have no way to compute that by hand, people actually had even tables of random numbers, believe it or not. People had like book with random numbers generated by hand, numbers which were uniformly distributed, and it was sequence which was used for testing of random things, okay, probabilities, which is now looks completely silly, right? But people had tables for sines, for cosines, for all the other functions, and also for random numbers. Okay? They had table of random numbers, which by definition is not random, obviously, because you type it in the book, so they stop being random. They repeat themselves all the time. But the point is that he developed computers and he developed methods which would be useful for computers. And the idea of Monte Carlo method is practically very simple and universal for solving almost any problem. Okay? Any problem that you can test randomly a few basic points in your solution. You might have, let's say, some mathematical problem which is described by some particular complicated surface or hypersurface or some function or anything of that kind, okay? So you want to know how this function looks like, and you have no opportunity to check it point by point. Okay? You cannot measure that every single point. And remember, all of the problems of optimization are that kind of problems where you have like cost function of some kind, you want to minimize it or maximize it, and you don't know what that cost function is everywhere in hyperspace, but you can measure that at particular point or neighborhood. Okay, this is all you can do computationally. That will not be super expensive. You cannot do that like point by point everywhere because you have infinite number of points. So there is no way that you will build it continuous surface, right? This is a big problem for all engineering and computational problems, that you cannot build the entire surface. You can measure it at particular points. So his approach, Monte Carlo approach, and you know, Monte Carlo is famous for. Yeah, this is too, but mostly for its casinos, gaming, gambling, that kind of thing. So this is where the name is coming from, gambling, random stuff, that stuff. So the idea is that instead of trying some particular grid to measure that surface, hypersurface or whatever, which will be super computationally expensive, you need like 4 in 4 in 4 loops, like to measure that in n dimensions, right? Sample that in a few points. Like pick point here, point there, randomly, uniformly divide these points, get these measurements. Can you get whole picture just from these points, from these measurements? Obviously you can't, okay? This is the correct answer. You can't figure out the entire surface. But can you approximate how it looks like overall? Kind of, depends on number of points. If points, you have a lot of points, then you can do that better. If you have a little bit of points, then you can do it in very crude way. All right, this is the overall thinking. But having this endpoints sampled in all kinds of places, and you have overall idea how the surface might look like, can you predict where do you need to sample more to get a better idea? And here is very simple kind of idea behind the next step after basic Monte Carlo method, which is particle filtering that I will be talking about. The idea is that you can do sampling sequentially, measure more in places where you have more change. This is the idea. Makes sense. Let's say if everything is flat, you don't need that many points to measure that neighborhood, okay? It's all flat. So if you measure a few points, you can put straight surface through that, some plane through these points, okay? This will be close enough. But if it is changing all the time and you have like 1 point here, 1 point there, 1 point here, 1 point there, then this neighborhood is changing a lot. So you need more sampling points to identify these big changes. That's it. This is the general idea of particle filter. Measure more where it changes more. That's it. This is how it works. So all of the Monte Carlo methods practically based on very simple idea behind them. All right? And if you understand the overall idea, you can apply the same idea to multiple different problems. Just measure more wherever it changes more, okay? And then you will have better accuracy everywhere. On flat areas, you will have a few points sampled. On changing areas, you will have a lot of points sampled. And from these points, you will be able to replicate the original surface close enough. Now, you can repeat it until you have enough information and you don't get any additional information from that. But this works great for problems which are not directly solvable, where you need to have like 500 for loops to solve it on a big grid, okay? So instead of that, you can choose that. It will have much less points actually eventually. And it's not that expensive to check all the Monte Carlo approach. Monte Carlo approach is less expensive than kind of having grid on all the possibilities, which typically is not even solvable for many problems, okay, multidimensional problems specifically. Now, bad thing about Monte Carlo method is that you need that the error decreases as square root of 1 divided by n. So approximately. So what does it mean? Square root 1 divided by n. N is number of samples that you checked for computing your problem. And this means that if you want 1-digit improvement in your accuracy, the result, you need to do 100 times more points. It's like 100 points more for 1 digit. And this is not great, okay? Because this is changing as square root. 1 divided by square root of 100, the error will practically be divided by 10 every 100 additional trials, which is not great. And this is why this is good for problems where high accuracy is not really required. You're just estimating something, you are approximating something. You need fast solution for a problem which otherwise is not solvable or too computationally expensive. To get quick approximation of where the solution should lie. It will not give you like super accurate result, but that's fine for most problems, especially in engineering, where we have tons of different tolerances, we have noise, we have all the disturbances and other things. So in that case, you cannot look for like super precise accuracy. 0.000 kind of accuracy. You just want quick approximation. Any questions on that, on the overall idea?
I have a question. Do we use something like Nyquist sampling method to apply to the Monte Carlo?
Nyquist are you talking about? So first of all, you're talking about Nyquist sampling theorem.
Yeah.
Which is like you need to have highest frequency will be half of the sampling frequency to reconstruct it exactly. This is the Nyquist channel theorem, right? This is what you're talking about. Now, this is talking only about even sampling, which means even intervals, equal intervals between the points. This will be true only for equally spaced samples. It's not true for any kind of sampling. And this is why you have other techniques which can give you higher frequencies with the same number of points. Sparse sampling. It's called compressed sensing. So compressed sensing is when you are kind of varying the spaces between the dots in a way using similar idea to this one, where you're sampling more where it is changing more, and then you're sampling less where it is flat. Then you can get higher frequencies with the same number of points and reconstruct them back completely. Okay. But this is kind of different because here I'm saying don't change the sampling rate. I'm saying sample randomly. This is kind of different. So just sampling randomly, uniformly distributed on a particular interval. And then you get the solution, which is not possible in real time. So it's only for offline data, not for online data. So this is not the same thing. Okay, any other questions? Okay, so let's try something standard in that Monte Carlo methods example. For example, how to compute pi. You want to approximate pi using Monte Carlo methods. And to do that, you are building some sort of square, like the square on the left. You inscribe circle, and the square, let's say 1 by 1. Okay, you can think about that as 1 by 1 square, which means square is area 1. And you inscribe circle inside of that, which is touching that square. So the radius will be obviously 1/2. Okay, if the square is 1, and the area will be pi r squared. This is formula for area of square of circle. Remember that formula? Pi r squared. Hopefully you can compute the actual ratio between like 1 square and pi r square, which will be 1 divided by 2, which is pi divided by 4. Okay, so the ratio will be pi divided by 4. The ratio of circle to square. Okay, so far? So we are trying to estimate that number, pi divided by 4. So to estimate pi, obviously we'll just multiply it by 4, and then we will get estimation for pi. Okay, so far? So here's how we do that. So this square is 1 by 1. We have uniform distribution of 1 from 0 to 1, numbers from 0 to 1 in both dimensions, in x dimension and y dimension. We throw particular dot at random number between 0 and 1 in x and y coordinates, okay? And you will have all kind of black dots like here, okay? You just throw in randomly, uniformly selected dots anywhere in the square, okay? Is it clear what I'm doing here? I'm just throwing darts, okay, into that square and assuming that I'm not targeting the center, but targeting everywhere in the square uniformly, I'm getting all these black dots. So the pi divided by 4 is ratio of points which are inside the circle compared to all of the points. This is Monte Carlo approximation. More points you get, like here, for example, more points you have, better your approximation is. It's just number of points inside versus all of the points. This is a ratio between area inside and overall area. Now, this could work for any shape, not only circle. You can have any kind of weird shape inside of that square. Doesn't matter. It will give you ratio between the area of that whatever shape and area of the square, always. So more points you have, better approximation you will get. And here is MATLAB code, which is actually computing that type of approach in a very simplistic way. So this is computing that for multiple types, number of samples. So I'm taking 100 samples, 200 samples, 300 samples, and so on until I'm getting to 100,000 samples, okay? This particular step size of 100. Which means I have like 100 dots, 200 dots, and so on until I get a lot of dots. Okay, hopefully getting higher and higher approximation. Practically for Monte Carlo, you need only the inner part of that for loop because you're doing that only once. Let's say you're picking 1 million dots and you want approximation for that thing, you're just skipping all of that 4 here. Okay, this is the actual computation of pi. So what I'm doing here, I'm starting with 0, which is how many dots I have inside. And then I'm throwing 1 dot in the for loop for 1 to 100. Okay, number of samples. I want 100 random dots, and I can do that like much more optimally when I'm vectorizing it, obviously. So I can just generate a vector of 100 random numbers from 0 to 1 uniformly. Okay, function rand, giving you a number between 0 and 1. Remember that function from MATLAB? So it generates some number between 0 and 1. If I generate that number multiplied by 2 minus 1, what do I get? Where this number is distributed? What is that thing?
What number you get?
So you're taking number between 0 and 1, multiplied by 2 and subtracting 1. Where does that distribute? It's still uniform, right? I'm not changing uniformity of the distribution. But where it will be distributed, like what range it will be distributed?
Saying 0 to 1.
0, 1.
0, 1? No, 0, 1 is rand itself, without multiplying by 2 minus 1. This will be 0, 1. If you multiply by 2 and minus 1, then how it will be distributed? Like what are the boundaries?
Minus 1 and 1.
From minus 1 to 1. So this is specifically talking about square of size 2. Means area 4. Okay. This is different from what I just said here on like side 1. It's plus minus 1 actually. But you can do that for 1 as well. I mean, it doesn't matter really. You will get the same result. But I just wanted to show that you can transform your uniform variable to make it any interval you want. Okay, it doesn't have to be between 0 and 1. It could be from minus 15 and 72. Whatever you want. You just multiply it by some number and subtracting some number, and then you can linearly transform it to any range you want. And how do you know the range? You're thinking 0 times 2 is 0 minus 1, so left boundary is negative 1. Okay? If you want negative boundary to be minus 5, then you're doing here minus 5. Okay? And then right boundary is 1 times 2, which is 2 minus 1, it will be 1. But if you want something else, substitute here 1 times whatever that number x alpha, whatever, minus whatever that number that you computed for the left boundary, right? And then you will be able to compute the right boundary where you want it to be. So you can decide on the range for these random numbers programmatically by that linear transform. This is the idea, okay? But in that case, it's like from minus 1 to 1, y is from minus 1 to 1, so you'll get some random dot. You compute in very simple condition, is it inside the circle, which means x squared plus y squared less than radius 1, okay? Because radius of the circle will be 1. If the square is 2, the radius is 1, okay? Is it clear? The side is 2, so radius is half of it, which is 1. So the circle should be radius 1, which means that we are estimating pi r squared, where r equals to 1. So we are estimating directly pi. Okay. Now, if this is true, which means it's inside the circle, it's less than the radius squared, which is 1, then inside adds 1. Okay, so you elevating that number by 1. Practically, you're counting how many points are inside. Compared to how many total points? 100, okay? So total you have 100, which is the number of samples, and inside is the number of points which are inside the circle out of the total number of samples. So if you divide inside by samples and multiply by 4, because the area of the square is 4, you get practically approximation for pi. Okay, this is your pi value. Any questions on that?
You're taking the ratio of the area of the circle.
Yes. The overall area.
Overall area. And you're setting that equal to pi?
This is pi, yes, because it's pi r squared and r equals to 1.
Yeah.
It's pi divided by area of the square, which is 4. multiplying by 4. You get pi. Okay. So here's how it will look like for different number of samples. So the x-axis are samples, and these are different solutions to that thing, okay? So each one of these dots at the vertical line will be for the same number of samples. You'll get different, obviously, solutions, different approximations each time, and they will be distributed widely initially when you have only like 100 samples, 200 samples, and they will become like narrower and narrower variation when you have a lot of samples, okay? When you get to these big numbers, but it's still not zero, okay? It's not converging to very, very, very narrow. You need a lot of different, like a lot of samples that will be very narrow, okay? So approximation will be, this is the correct number, this like horizontal line is a correct pi number, and distribution of points is the numbers that I'm getting from random simulations, kind of numbers, okay? So it is converging to that number eventually, but very slowly, okay? This is what you could expect from Monte Carlo methods in general. That convergence will be slow to the numbers that you want, but even with that number, you can get pretty good approximation between like plus minus 0.01 or something, okay? With that number of samples, you can approximate it. And it's not easy shape to approximate actually, because pi is transcendental number, difficult to get. Any questions on that example?
So any addition of 100 points will increase the accuracy by 1 degree.
Is there any other way to plot the graph, like d² to find the
Yeah,
best
or you can-
approximation?
Technically, I'm plotting all of the dots. People practically compute just mean of the dots. And mean of the dots will be much closer to that actual line. Okay? So mean of these dots at particular number of samples will give you approximation of pi. So you're just practically taking all of these dots at particular vertical line and computing mean of these dots. Okay, so it's like you're taking bunch of points, you repeating the same process multiple times, and you're taking mean of it. So mean will give you pretty good approximation the overall value. Okay, but take small window here, compute to there, for example, the small window, compute a few times in that window, average, and you will get better approximation. So Monte Carlo methods are always using averages of numbers, and we will see also why this is correct way to use things in a second. Any other questions?
Would it be better like using v² approximation,
This square approximation for what?
or like to find the pi, the target you want
Square approximation to what?
to the samplings? Yeah, any samplings, right? And
No, like look, this example is not something that you compute in Monte Carlo. In Monte Carlo, you compute only 1 point out of that example. Okay, I computed like many points here, but technically you can compute only 1 point to estimate pi. Let's say you're picking here that last number, 100,000, okay, and you don't run that for loop, you run only that one number, okay, and you get all kind of samples. Out of that, you get also one number. This is your estimation of pi, that one number. You don't have anything to fit to. Because this squares is when you have multiple things to fit to. Here, you get one answer. I'm just showing you that these numbers, like answers, might be very widely distributed, okay? If you compute it multiple times with different random samplings, okay? So they could be all over the place. One time you get one number, another time you get different number for the same computation, same loop. Because you have that randomness here, right? So that randomness, each time you'll get different answer, different approximation. They all will be close to 3.14, which is close enough to pi, but they might be all kind of numbers close enough. This is the same, that you never get the same number again. And more times you run it, more numbers you will get. Eventually you can do average on them if you run that enough time, and you'll get better approximation from the average, because should have average, which is pi. Okay, by definition of what probability is, right? Because exactly probability of infinite number of points inside and outside will give you exact number pi. So it should converge with infinite number of points, but you will never get there, right? This is the same.
Actually, you run it one time and you generate one dot.
Mhm.
And I wonder, can you like you after sampling all the dots, right? Can you just like put those dots in a record? So you use something like least square approximation to
You
find.
don't need least square, you just need mean.
Right.
It's much simpler than least squares. You just compute average of them. Your average will get you better approximation if you're doing the same process multiple times.
Yeah.
Exactly, repeating same exact process multiple times. Just average on the results, you will get better approximation. Okay?
Each outcome here is an approximation of pi. So every
Yes,
time you
each
do
dot
it,
is approximation of pi.
every time you do it, you're getting something
Yeah.
that's approximately pi.
Yes.
So take all of those approximations one time and just do average.
Yeah.
You should get pi. Close to pi.
Yeah, you still will not get exactly pi, but you'll get something close. Okay? So here is the idea of Monte Carlo integration. This is the basis for all of the particle filtering and other algorithms related to sequential Monte Carlo. And you have like full books on Monte Carlo methods in engineering and how you apply it to different kind of problems in computer vision or otherwise. So here's the idea. This is something basic from probability theory, which hopefully you've seen before somewhere maybe, but even if you didn't, that's fine. The claim is if you have random variable, and we will call it x, the p of x, which is probability distribution function of x, like think about some sort of Gaussian shape or uniform shape or whatever the shape is. So for any function, if you want to find mean of that function or expected value in probability theory, remember what expected value is? Practically, you can think about that as mean of the function, okay, of that x, and we use that E symbol for expectation, okay? So expected value of that f will be integral on interval from a to b of fx times p of x. So these are kind of weights, like probability distribution is weights of that function that you give for each particular possibility for that function value, okay? So it's weighted average. And if you remember, we learned about that kind of formula as inner product between these two functions, okay? So this is inner product between f and p, all right, for function space. Now, so that inner product is expected value of the function f. But now look what happens if your p is uniformly distributed on that interval ab, okay? So what is uniformly distributed? That means the value is 1 in that interval, or it's actually not supposed to be 1. It's supposed to be 1 divided by a divided by b, but it's proportional to 1 in a sense, okay? And then 0 otherwise, okay? So what happens is that you practically multiply that thing by a constant, which is like a 1, right? And in that interval, what happens? Every point on function f gets equal weight, right? Because it's uniform distribution. So that integral could be approximated by just mean of all the points that you're taking on 0, 1 interval. And any function could be scaled to 0, 1 interval, okay? This is the overall idea of Monte Carlo integration in general, okay? That you will have likelihood of 1 for all of the points. And if this is likelihood of 1, then integral of p times f is practically integral on f. So you can compute integrals on f in these intervals, just using the average of all of the points that you sampling it at different points. So sampling it randomly at different axes here, okay? And instead of computing integral, you're computing just average of all of these points. That's it. Let's take some simple example on that simple interval of 0, 1. Okay, let's say you want to compute integral, or to estimate integral of cosine of x squared, which would be probably not very easy to compute analytically. if even possible. Do you know if it is possible to compute analytically cosine of a square? Maybe. Maybe it's possible, I'm not sure. Calculus was a long time ago. Whatever. You can pick any other integral, okay? It doesn't matter. Let's say you have the function, okay? You have that interval. All you need, you uniformly sampling cosine of x squared at different points. You're computing cosine of 0.1 squared, cosine of 0.75 squared, cosine of 0.68 squared. You're simulating 1 million points like that, okay? Generating all kinds of random points from 0 to 1, putting them inside x, computing cosine x squared. So you get a bunch of points. All you need to do, you're computing average, which is sigma of all of these values divided by n. And n is the number of generated points, okay? And this one is uniformly distributed from 0 to 1. That's it. This is your Monte Carlo estimation of that integral, all right? And this is how you get that in MATLAB, practically, a few lines of code. Let's say you're generating 1 million points, which is very simple. Then you're computing y at these points, okay? And then you're just computing mean of that. So here is the actual result of integration, and you're doing that probably analytically. I'm not sure how computer is doing that, but whatever, this is the actual correct answer. And this is the answer that you get from that computation. This is what MATLAB shows you by running that code, which is kind of close. Okay, this is like fourth digit is a little bit different. That's it. Okay, so you got pretty good approximation for the integral by computing Monte Carlo methods. Any questions on that?
So
Yes.
the value of n determines how good your approximation is.
Bigger the n is, it's more computationally expensive, more accurate. Okay, but to get like approximation better by 1 digit, you need to multiply that number by 100. So it's complicated. You need a lot of computations here. All right. So it's not super efficient method, really. So now what I want to talk about is particle filtering and using that for applications that I used that in my PhD a long time ago. Now I can't believe it, almost 20 years. So the idea of particle filtering, as I said, is using Monte Carlo methods, which are called sequential Monte Carlo methods. You're doing that step by step. Instead of throwing all of these million points immediately, you're still throwing some number of points, but then you redistribute them and trying to find where you need more points to sample. This is the idea. And since for visual tracking, you need to identify location of particular target, particular object in the video sequence, you can do that frame by frame. You can move it, you can use some dynamical modeling that we used in state space, you can do all kinds of other things. So hopefully this will connect practically like 5 different topics that we already talked about in previous lectures in that one overall idea. And I'm not getting into depths of the math here. I'm just telling you the overall ideas that you can apply practically almost to anything. It's not specifically for visual tracking. Okay, so here's a problem that we are trying to solve. You have some people walking on the lawn somewhere. Okay, you have some arbitrary targets that you want to track, and you have selected the target that you want to track, and you want to find trajectory of the target in the video sequence. So this person will go somewhere to the right. Okay, you want to find the trajectory, which means where at each frame that person is. This is a problem. Now we will assume that the object or target is not jumping too much between the frames, which means it's smooth movement, not disappearing, reappearing somewhere else, not jumping from frame to frame, okay? So it's all kind of continuous movement, which means that the search region where we're searching for the target is close enough to the previous location of the target, okay? It's not like all over the place. Otherwise, this would be called detection problem. So it will not be tracking problem, it will be detection problem, object detection, different kind of problem. You detect object based on particular features that you're looking for. instead of tracking the object based on where it was in the previous frame, right? So this is the difference. And you have so many different solutions for these problems. So they start with that cycle, which is initiated by prediction. So you try to predict where it could be in the next frame. You don't see the next frame yet. It never came. So you're thinking about it as real-time processing, okay? And the idea is that you can assume something about the motion of these targets. They could have constant velocity or constant acceleration, or maybe they're not moving that much, and this is some sort of Brownian motion around the same point, so they are moving all over the place, but randomly in all kinds of directions. So you can assume something about their kinematics, which is kind of more physics part. And these kinematics models could be written as state space models. I will show you how in a second. But given the state space models, what you can do is use prediction equations. And for prediction, you can use Kalman filter or particle filter or many other filters, PhD filters. You have probably dozens of different types of filters, IMM filters, you have JPDAF filters, you have all kinds of filters which are doing estimation of the objects in all kinds of conditions. Some of them are better for linear models, some of them are better for kind of changing dynamics models, some of them are better for some other properties of the motion, okay? But each one of them has particular properties, and again, I'm not going into details of that. But for example, Kalman filter, probably the most famous one. Kalman has like 100,000 citations to his paper. And interestingly enough, has very interesting history around it as well. Have you heard about Kalman filter? Okay, so Kalman filter is the most famous filter in engineering, actually. It's used in so many applications, again, like 100,000 citations probably to the paper from other papers. So what happened is Kalman, when he developed that in probably like 58, something like that, he tried to publish that in IEEE. At that time, it was not IEEE, it was something else. It was called IEEE's Institute of Electrical and Electronics Engineers or something like that. But at that time, it was called something else. Same organization which became IEEE, at that time was called something else. It was with A something. Association of American Electrical Engineers or something like that. Whatever it was, this was same huge organization with tons of journals and other things for that time in like almost 100 years ago, in 50th, previous century. So he tried to send it to one of the most famous controls journals in that older IEEE, and it was rejected. So he sent it to another journal in that area from that IEEE, and it was rejected. And people said, like, this is nonsense, nobody will use it, this is not interesting, okay? And then he sent it, he was like really mad at them and said, I will never publish again with IEEE. Later he got medals from IEEE and other things like that. He said, like, I'm not dealing anymore with that organization anymore. And he sent it to Mexican journal that nobody heard of ever. Now this journal is famous for having his paper. This is like claim to fame of this journal. This journal became famous for this paper. Just one paper. Nobody published that, anything else in that journal. So his paper is extremely complicated to understand. It's like you have full books explaining what this paper is actually saying, all right? It's difficult mathematically, all the theory of Kalman. But this is still very useful. People are using that all the time. So you can use all kinds of filters, including particle filters, to predict next state without measurement. And then when you get some measurement, you can compare. And in terms of images, we talked already about some of that stuff. So we talked about normalized cross correlation or image Euclidean distance, where you're comparing patch from the previous frame to your new estimated location. Like, is it there? Is it close enough? Okay. And this will give you some sort of weight, like how close it is, correlation kind of measure. Is it correlated? Is the patch correlated to where I'm searching for it? If it is well correlated, this is most likely to be the correct location, okay? If it is not, probably you need to look somewhere else, maybe nearby somewhere. Okay, so you need to search around somehow, okay? And you have all of this kind of measures where you can fit features, or you can fit patches, or you can fit all kind of other things. You have tons of papers which are describing how to compare patches between the images. This is a matching. You can do also all kind of color matching, like mean shift, model-based stuff. You have all kind of ways to compare two images and to say how similar they are. Okay, so this is a matching process. And finally, you have estimation process, which is saying, oh, based on all of these measurements that I've done, where is the actual object? Okay, pinpoint the centroid point. And this will be your next point on your trajectory. Okay, and then you repeat in the cycle again, trying to guess what will be in the next frame, trying to measure all kinds of things in that next frame when you get it. Okay, and based on all of these measurements, you're trying to estimate where the object is. This is a loop for visual tracking in general. And here's a state space model for what I have used. And this state space model is very simple. It includes a few variables: location of the centroid, velocity of the centroid, and scale of the object. This object could be kind of zoomed in and zoomed out, so you can get closer to the target or farther. The camera can kind of zoom in and out, or object can move farther or closer, okay, in the video sequence. So you need to know what scale you have, where the object is located, and how fast it moves. You can add also acceleration to that or some other things, but I haven't went that far. It was enough to estimate velocity. So general state space model, if you remember, it's next x or present x equals some function of previous x. And also maybe some noise, because I have some noise in the system. And this noise, I will assume that this is white noise, Gaussian noise. So it's zero mean, which means I will know the location approximately, I will know velocity approximately, I will know scale approximately. And this approximation, which means what I don't know about the actual model, will be modeled with that noise. Right? So here are a few simple examples. Constant position model, this is the simplest one. It means the next state is the exactly location of the previous state plus some noise. And same thing for y coordinate. For x, y coordinate, it will be practically same location plus minus some noise. So everything I don't know about the motion is just noise. Do you know what is the name of that type of model? Has very famous name. Where you assume that some dot is moving just based on the noise, white noise kind of thing. So it's previous location of the dot plus white noise.
Brownian motion.
It's Brownian motion. So this is Brownian motion model. Practically, it says it's kind of like speck of dust in the water, okay? It's just doing all kind of weird motions. So it's Brownian motion, okay? Now, this is something more clearly mechanical. And if you learn kinematic equations in physics, this is how kinematic equations look like. So next location is previous location plus speed times delta t plus some noise. In kinematics, it means that you are moving with constant speed in particular direction, okay? And this is your step size, which is like deltas of time multiplied by velocity. Now, previous velocity is the same as present velocity. This is how it works, okay? Which means up to noise. Velocity still can change, but these changes will be due to some uncertainty or noise. In a sense, okay? It's just something that I don't know about how velocity is changing. So I assume that velocity is not changing plus minus some noise. Bigger than noise is, bigger I allow these changes to be, practically. So I'm including everything I don't know in the noise part, right? And then I'm assuming something about distribution of the noise. That's how it works. All right, so this is state space models for dynamics of the system. And this is how I will predict where the next position should be. I will just generate some noises here. I will use previous velocities that I recorded from previous frames, estimated from previous frames. And this will be my estimation of velocity and estimation of state. That's it. Okay. And every time I will iterate on the state equations. Okay. This is iterative, right? I can compute the next state based on the previous states. That's it. This is my prediction model. This is what my Kalman or particle filter or any other will get as its input. This is my model. So here's how it works in particle filtering. Let's say I want to track that tank object. All right. I generate n particles, and particles will be these windows that I put on top of that picture, which means I will generate, let's say, 5 particles, 5 windows, which will be exactly the same place, because I'm selecting that initial place. So I'm selecting the object, so I know where it is. I have no uncertainty about location. So in some cases, I do have uncertainty, so I can distribute them a little bit around that object, but that's fine. My initial step, I'm selecting the object, okay, by hand or by whatever detection algorithm, all right? So the next step is to do prediction, where it could go. And assuming that I know already maybe some knowledge about like what direction it's moving or some kinematics based on that state space model, okay? What I'm doing, I'm distributing these windows randomly. So it's use dynamical model plus noise. And this is where these windows will end up. Before I have the next frame, it's still like frame number 1. Okay? I don't know what will be the next frame and where it will be in the next frame. But I just spread it around using Gaussian noise. Okay, that's it. Plus constant velocity, whatever it was estimated from previous steps or prior knowledge of some kind. Okay, it could be starting with 0, for example, initial conditions. Then you have 0 velocity, nothing. Okay, so next step that I'm doing, I have frame 2. So it moved. So it was here, now it's there. You see, moved from here to there. Now I have for each one of these windows to measure how close it is to the original object. Okay, and as you pay attention that there are different scales, sizes, right? So I changed also the scale because it's part of my state space description. Their location is different, and each one of them is assigned also some sort of velocity, which you cannot see here, but it's kind of part of the particle. Okay, you have that velocity inside of it. So what I'm doing here, I'm assigning weights to each one of these windows, how close it is to the original image, original patch. Using normalized cross correlation, using whatever other Euclidean distance, whatever you want, okay? Some measure which is telling me that this one is very close, right? This window, which is 0.85, and let's say it's like normalized between 0 and 1. This one is kind of partially close because some of it is inside, right? This one is horrible because it's like catching only tiny tail of it. And this one even worse because it's catching only the tiny part. So it's not similar at all, okay? So all of them, these two are horrible. These ones are kind of close. This one just incidentally close. Could happen all the time, happens all the time. So you have something which is not very similar to your image, but gives you high enough weight, high enough importance, whatever it is, okay? Because of all kind of artifacts that might look like that image, but it's not. So you have all kind of errors and mistakes on the way. But what happens is that based on these weights, you can find weighted average of all of the centroids of these windows. And this will be that weighted average, it will be here. This is my estimation of where that thing is. Okay, for that frame specifically, before I've got to the next frame. But now I need to prepare for the next frame. So what do? I resample, and I sample more where it's more likely to find the object, which means I need to take all of these red windows on the left, which are not very similar, and redistribute them closer to the right where I actually have higher weights. And again, it's not telling you where the object is, it's just saying you that this window is much more likely to include the object than these two. So I need to take these windows and to move them here, okay, where it's more likely. And in particle filter, it happens automatically. You have algorithm which is doing the resampling importance resampling. It's like sequential importance resampling algorithm, which is automatically takes all of these windows from the picture and drops them, and you will have just more windows where it needs to be automatically. Okay, you have algorithm for that. Again, I'm not showing it, but this is SIS, sequential importance sampling. It's redistributing windows that way, and you'll end up with windows, more windows around regions where it's more likely to find the object. Some of them will still be off, like the window at the top. Okay, it was horrible window, but you haven't redistributed it. It stayed, so it's still searching in other regions. And more samples you have, more particles you have, more likely you to catch all kind of other things, which is fine. I mean, they eventually will disappear because eventually they will lose track of the things and will be redistributed wherever you need them to be, okay? But now you repeat the same process, you're shuffling that, this Gaussian noise, okay, redistributing it again. And then for the next frame, when you have new measurement, you'll be measuring in these new frames, okay? Again, this works only when you have enough samples. If you have only a few windows, this will not work, it will lose target very soon. But if you have like a few hundreds of them, or even like 50 of them, then it's likely that it will track pretty nicely your object, okay? And all these particles will kind of follow that object. Sometimes something will stick here and there, but eventually they will also jump to that object and will, again, search around it. This is the overall idea of particle filtering in general, all right? So try to think how you can generalize it to other problems, because this is a very specific problem. But this is overall algorithm for estimating any kind of probability distributions in general. This is what particle filter is doing. It takes original estimation of a priori distribution, measures that with a few particles, which means samples a few dots on that original distribution. Let's say you have that 5 dots. Then you shuffle them with some sort of random noise, and you can use any kind of random noise to redistribute them somehow, like where to measure them next time. Then you get updates, which means you're measuring how strong that value at that point is, and could be strong or weak. And then you again sample same 5 out of them and getting new distribution, new estimation for your distribution based on how strong that was and how many times you're sampling in this locations and this location. So you will sample more where the peak is, essentially. This is how it works, okay? Where it's more important, more probable to be, okay? You're sampling more probable regions instead of sampling uniform. You're starting with uniform distribution, typically, okay, sampling everywhere equally, and then you start to sample more and more where probability becomes more and more important, more strong, okay? And then you're estimating peaks much better. And typically in most problems that I'm familiar is you're looking for peaks, highest probability, highest likelihood. It's that kind of thing. And this is what particle filter is doing. It's finding the modes eventually, okay? And then you iterate on that same process. Now, this is how the actual mathematical formulation looks like. And this is why I'm not going into that, because without getting into probability theory, it's a little bit complicated to explain even notation of that. So this is a prediction step where you're using state space model kind of thing, okay? So like next X given previous X state, and then you have that measurement, which is giving the W weights, essentially computing normalized cross correlation or whatever other measure to compare between given state. You have some measurement, and then you're computing that weight as proportional to that number, which is probability. And then you're resampling particles using SIS, and then you get practically average, which gets me to the same formula practically as we had in Monte Carlo. And this is why this is sequential Monte Carlo method. This is practically average on that thing, weighted average, all right? Because W divided by N is that P that we had before, okay? Practically, this is all I wanted to say about it. Don't worry if you don't understand any of that stuff. It's fine. If you are interested in that, we can talk about it more. If you're interested in Kalman filter, this is next semester course. Any questions? Yes.
So this method is purely data driven. So,
Data driven, exactly.
so for some particular cases, the sampling, I mean, how you distribute the sampling in the prediction stage, can you constrain it by maybe a physical equation to just maybe reduce the computation and how expensive and all that?
So you can constrain it in two different points. One point is by your model. Your model is physical constraint on how the object can move, okay? Or change. It doesn't have to move it and it's not moving or it's something else, depends on the problem. So what happens is all of the prediction problem is defined by state space. State space are dynamical equations describing dynamical properties of the system, whatever the system is. You can constrain it whatever way you want. More than that, you don't have even to use linear state space for that purpose. Why? Because I can use completely non-linear state space and just randomly sample out of that non-linear state space equations. These equations will be not linear equations, will be like x squared plus cosine of whatever, plus some sort of truncated noise, which is not Gaussian at all. And so I can do any model I want, as complicated and complex as I want, okay, as close to reality as I want. This gives you constraint on the dynamics of the system. This is first component. Second component, when you are doing measurement, you can measure that in also very constrained ways. So you can limit your measurement to particular location, or again, depends on the problem, what you need to do. So you can constrain it in multiple different ways. So yes, you can impose additional equations and constraints on the problem, and it still will work. And you have like 1,000 different types of particle filters that people invented through the time. At a particular moment of time, I talked to my mentor about publishing on particle filter, and he said, like, never use the word particle filter again. I talked with one of the editors of IEEE journal on control something, and he said, we are not publishing any more particle filters because you have so many papers on particle filtering that we just don't want to take anymore. This is how it worked. And you can use sequential Monte Carlo instead of particle filter now. Same thing, but different name. Okay, any other questions?
Question.
Yes.
The method you're using to track the object, if there were the same object around,
Yes.
would it be able to track that sensor object, or would it be lost because it has similar?
So I'm tracking the bounding box, which is practically centroid of the object and scale. So I know how big the object is based on the particle filter prediction. I have scale, I have coordinates of the centroid, and I have velocity of the object. I'm not tracking the shape. I have different algorithm which is tracking shape of the object, which is contour around it. This is different, yeah. Okay, any other questions? Thank you, and next time we will have online lecture on Zoom because I will be out for a conference. Tomorrow morning I'm flying to Virginia, and then we will have 1 week break. And then after that, we will start presenting projects, okay? Questions? All right, thank you.